Hello, beautiful humans. Today we are going to talk about complex systems of inequalities. So unlike our systems of equations we talked about last week, where we were looking at specific points of intersection, now we're looking at regions that would satisfy both of our inequalities or many inequalities, as the case could be. So a system of inequalities is two or more inequalities, and they represent a range of solutions. So for example, if you have a curfew of 10 o'clock and your parents say you better be home before 10 o'clock, you can come home anytime before 10 o'clock. This is a range of values that would prevent you from getting in trouble, right? So if you think about a word problem, often in real life, there are many, many examples of inequalities representing whatever the case may be, many, many different things. But in this case, we're talking about a job and how many shirts and pants you can produce, and the idea being here that obviously this person would like to make as much money as possible, right? So they create inequalities to represent the various restrictions they have, and then they can use that information to find what would make them the most money profit, right? We would do a whole set of word problems if we were in class for this. But yeah, take my word for it, this happens in real life all the time. The area that gets shaded for all of the systems, so this one has three different linear systems, and this region in the middle that is shaded for all of them, we call the feasible region. Okay, so again, this would be the feasible region. Feasible meaning that it has the solutions for all of our systems. So it's the area where we can find solutions to whatever the problem is we're trying to solve. And again, every single point in there represents a solution to this problem. All right. Okay, so the first thing you want to do is graph your function. Also, don't forget we have to take into account greater than or less than is going to give us a dashed line, because the line is actually not part of the solution, right? We have to be just greater than or just less than. The line will not give us values that would satisfy our inequality. If we have greater than or equal to or less than or equal to, now we have a solid line, because the values on that line will also satisfy our inequality, give us a true statement. So if you test a point on the line, it will give you a true statement if it's greater than or equal to. It will give you a false statement if it's just greater than. Hopefully that makes sense and is a review concept. All right, so first we have all right, so let's look at this first example. We're going to graph these functions. We're going to test points in the various regions so that we can identify the feasible region. For time purposes, I went ahead and graphed these ahead of time. We have a quadratic function with a vertex at +2, +4, and then this is being compressed by 1/3. So I created a little XY chart there so you could see what was happening. So normally when we go over 1 squared is 1. So, but in this case, we're going to take 1/3 of that. We're only going to go up 1/3. It's not really a clean point to graph. So I jumped ahead to 3, because 3 squared is 9. 1/3 of 9 is 3. So when we go over 3, we only go up 3 instead of the 9 we normally would go up. That's how I graphed my quadratic. It is a solid line because it's greater than or equal to. And then I had to graph my square root function. My square root function has a locator point at -2, +8, and there's no stretch or compress. So I know that I go over 1, up 1. And then the square root of 4 gives me 2. So when I go over 4 from the locator point, I go up 2. And then the next one I jumped to was 9, because the square root of 9 is 3. So when you go over 9, you're going to go up 3 there. Okay, so that's how we graph this. This is going to be a dotted line or a dashed line because y is just less than, not or equal to. So that means that line, again, not included in the solution. All right, so now we need to kind of define what different areas could our feasible region be in? Well, we could have below the square root function and above the quadratic function, that little area in there, the yellow region. So let's pick a point from there. That would be like the point 2, let's do 2, 5. Yep. So we could test the point 2, 5, and that would be, again, in that below the square root function and above the quadratic function. All right, so that's one option. We could also test within the quadratic, but above the square root function. So that would be another location. So we could test a point, say 0, 10 to have friendly numbers. Okay, so we could test that region. Again, that would be above the square root, but still inside the quadratic. And then we could also have outside the square root and underneath our square root function. So we could have outside the quadratic and underneath the square root function. And then last but not least, we could have, let's pick a point for that actually first. Let's pick a point we could test for that. We could test the point 0, 0. That looks like a nice friendly point to test for that one. And that would be, again, our blue there. And then also, we also have one other region we have to test, which would be outside of the quadratic and above the square root. Okay, so outside the quadratic and above the square root would be values like, let's find another color over here. So outside the quadratic and above the square root would be over here values, right? So this, let's find a good example. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. Let's see. 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we get to, what did I say? 7, 12, I think. Let's try that point. 7, 12, and we can test that in the pink region. Okay, so what that means is we're looking for the area that is going to make or give us true solutions to both of these inequalities. So we're going to test them. If we get a true answer, so if it makes one of them true, we're not done. We have to test it for both of them. However, if we get a false statement out of either one, then we don't have to test the other one because it's false for one, so it's not going to be my feasible region. All right, so let's start with our yellow point. I'm just going to plug this into the square root function because I think it's a little bit easier. So I'm going to say 5, my y value, is less than the square root of 2 plus 2 plus 8. All right, 2 plus 2 is 4, square root of 4 is 2, 5 is less than, is it 2 plus 8, which is 10. That's a true statement. Whoop, whoop, whoop. I don't know why I gave it an I. I meant a T. T for true. Cool. So now we need to check the other one and see if it's also true for my quadratic. So if I plug in 5 for my quadratic y value is greater than or equal to 1/3 of 2 was my x value minus 2 squared plus 4. 0 squared is still 0. 1/3 of 0 is still 0. 5 is greater than or equal to 4. That's looking to be true as well. All right, so once we have a value that's true for both of them, that should be our feasible region. We got really lucky here that we found it on the very first point we tested. So I'm going to test a couple other points just to make sure I didn't do something silly. All right, so let's try 0, 10. I'm just going to try it in my square root function again. But I anticipate that it's going to be false for my square root function if my yellow point is in fact true, because that's above the square root function. So I expect to get a false out of this. So when I do 10 is less than the square root of 0 plus 2 plus 8. Well, the square root of 2 is definitely less than 2, and 2 plus 8 is 10. So this value is definitely less than 10, not greater than 10. So this is false, exactly what I expected. Had we tested that point first, you wouldn't have needed to check it in the quadratic because it doesn't matter if it's true or false there. And in fact, it'll be true there because we know that inside the quadratic is where we're shading. So it will be true for the quadratic, but because it's false for our square root, it is not a part of the feasible region. All right, let's test 0, 0. Again, see what we get here. Okay, now when I test 0, 0 in the square root function, I would expect it to be true because that yellow region is shading below that square root function. So I'd expect it to be true in my square root function. So I'm going to go ahead and check it in my quadratic because I just want to make sure that it's not a feasible region since we found the feasible region so quickly. So let's try 0 is greater than 1/3 of 0 minus 2 squared plus 4. -2 squared is 4. 1/3 of 4 is 4/3 plus 4. 4 and 4/3 was 5 1/3, right? Is definitely not less than 0. So that is false, just like I expected it to be. Again, if we check 7/12, we're also going to get a false statement. It's not in the feasible region. All right, so now that we've figured out all those color coordinating business and we found our actual solution, let's do it in yellow since that's what we did. We're going to go ahead and shade our feasible region. And that is our feasible region bounded by the top of our square root function and the quadratic, right? So in between those two is our feasible region. So any point in here, boop, 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 anywhere at all, is going to give us a true statement for both of these functions. Don't believe me? Test another point. All right, you try means you're going to pause, try this one yourself, see what you get. All right, so the first thing I did was graph these functions, again, paying attention to the fact that this symbol means we're going to have a dashed line, right? And then this symbol means we're going to have a solid line because it's actually equal to part of the solution. All right, so the first quadratic function I have here has a vertex at +3, -4. This is my dashed line quadratic. It opens up because it has a positive a value of 2. Also, every output has been stretched by 2, so we're going to go over 1, up 2. That's how I graphed that first graph there. Then my second quadratic function is facing down because it has a negative a value, and it has a vertex at 4, 0. We have an h of 4, but no k value here. So that's my second function. This is a solid line, again, because it's greater than or equal to, and then I graph that, no a value other than the negative. So when we go over 1, we normally go up 1, but in this case, we're going to go down 1 because of that negative value there. So now I've graphed my two functions. Next thing we need to do is identify what possible regions could be solutions here. Okay, so we could be above my first quadratic, right? So this yellow is above the first quadratic and below the second quadratic. So that's one option. We could be below the first quadratic and within, so let's say outside and inside rather for these quadratics. Okay, so for the yellow region, we could be inside both of the quadratics, right? Inside both quadratics. For the green shading, we would be inside our second quadratic, but outside our first quadratic. For the pink shading, we would be outside both of them. Okay, so then also don't forget, I should have, but I didn't. Ooh, naughty Kate. Oops. I should also check inside the first one and outside the second one. So we need to check all of these regions here to make sure that we find the feasible region. Okay, so I picked a yellow point, 3, -2. I tested it in my first quadratic and got a false statement. I don't need to test it in the next one because it's false for 1, so it's definitely not my feasible region. Okay, my green point, I picked 4, -4. I went and I checked that in my first quadratic and got a true statement. So now I need to check it in my second one because if it's true for 1, it could be true for both. So now I'm going to check 4, -4 in my second function as well. I also got a true statement. Fantastic. All right, now I'm going to check the value 6, 0 in my first function. I get a true statement. But when I go and check it in my second function, I get a false statement. So that's not the feasible region. All right, now I said I should probably check the blue as well, but because I know that the green works, the blue's not going to work, right? Because if the green is working, which is below that blue region, the blue is not going to work. But if you wanted to test a point like 3, 1, right? So if we want to prove it real quick, we could test 3, 1 and find out, and we would test it in our original, and we get 3 - 3 squared minus 4 is greater than 1. 3 minus 3 squared is 0 squared. 0 -4 is greater than 1. That is false. Again, could have predicted that based on the patterns you had seen so far, but for the sake of accuracy, let's test all our values. Okay, so what did we determine was the feasible region? Those green values. So I'm going to go ahead and remove all the other shading that I used just to kind of identify what regions. And I'm leaving the green to remind me where that area is. So it's outside of my first quadratic, notice outside of my first quadratic, and inside my second quadratic. So as this quadratic continues to grow this way, right, slowly and surely, all of the values that stay within it will be true. So the feasible region for this guy is going to be all of this down here. Hopefully this is making some sense as we're going now. All right, now we have another one. We have a circle here, and we have a quadratic. So we're going to graph our circle with a dashed line. Remember, this circle has a origin at 0, 0 and a radius of 5. And again, we're going to use a dashed line because it's not or equal to. And then we have a quadratic with a vertex at 0, 7. So we need to go ahead and graph those functions first. Okay, so 0, 0 is the origin of my circle, and then I have a radius of 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, and then again, this is a dashed line or dotted because the values on the circle will not make the statement true. So we're going to dash line our approximate circle here, like so. And then my quadratic function has a vertex at 1, 2, 3, 4, 5, 6, 7. It faces up, over 1, up 1, over 1, up 1. And it is a solid line. All right, when you look at these two functions, it is possible that we could end up with a no solution situation, right? Because we have regions that do not overlap here. So think about that. We could end up with a system with no solution. So let's think about our different regions here. We have inside the circle, but inside the circle would only work if it was outside the quadratic, right? It would have to be outside the quadratic and inside the circle. So this part's not going to work, right? Because it would have to just be outside the quadratic and inside the circle. So not outside the circle, so that region's not going to count, okay? Then we have this outside the circle, outside the parabola region, right? Outside. And then we have the inside the quadratic region. But I don't see any way for that to lead to a solution. So if we're in that pink area, we're not going to be able to pick up any part of that circle, right? So I'm not feeling like we got, I don't think the pink is really an option here. It doesn't make sense in the context of my problem. So let's just try some points. Let's try 0, 0. Test that out. So when I test that in my circle, I get 0 plus 0 is less than 25. Looking good. Okay, so that means that inside the circle is the area I want to shade. Cool, because I just tested a point inside the circle and it was true for the circle. So that is the area that's going to be true for the circle. All right, well, let's test it in the quadratic and see what happens. We end up with 0 plus 7 is less than, or 7 is less than or equal to 0. 7 is not less than or equal to 0, so that is false. So that means we must be shading inside our quadratic function. So I'm just going to pick a point inside and test that out. So I know my vertex is at 0, 7, so let's try 0, 8. Oops. So really what I'm testing right now is that pink area that we talked about before that doesn't really seem like it's going to give us a solution for the circle, but I'm going to try it for the quadratic and see, because I found out outside the quadratic doesn't work. Okay, so 8 squared plus 7 is, oops, not 8, that's my y value, not my x value. Try again for now. 0 squared plus 7 is less than or equal to 8. Okay, so that is true, right? 7 is less than or equal to 8. So what we just determined right there is that the area that we shade for the quadratic would be the pink, and we found out that the area we'd shade for the circle would be the yellow. Well, there's no way that these two regions could possibly overlap. So this is a no solution problem, because there's no way that I can find a point that works for both of them at the same time. So you can get no solutions. There's no values that would make this true for both of them. All right, last but not least, the next U-try problem. Again, we have a circle and a quadratic. I have graphed them out for you. Dashed line for our circle, solid line for our quadratic. I identified 4 different regions that we could possibly live in. and we're testing those out. I'm guessing that my 0, 1 was my green. 0, up 1. Yeah, that looks good. All right, so I tested 0, 1 in my quadratic, and I got negative 0 is greater than or equal to 1. Negative 0 is not a thing, but 0 is not greater than 1, so that's false. Then I tested a yellow point, 0, negative 1. I got 0 is greater than negative 1. True. So now I need to test that in my second function, which is my circle function. 0 squared plus negative 1 squared is greater than 9. No, false. So that didn't work. Let's try the pink region. Value that would be in the pink region would be 4, 0. When I plug that in for my quadratic, I get a false statement. So I don't need to check it in the circle. Then I'm going to test the point 0, negative 4. When I test the point 0, negative 4 in my quadratic, I get 0 is greater than negative 4. True. And then I need to check it in my circle. When I check it in my circle, I get 16 is greater than 9. Also true. Ding, ding, ding. We have identified the feasible region. So we're going to go ahead and delete the rest of those colors because they do not work for both of my functions. I'm going to go back to my blue highlighter because everything underneath the quadratic or within the quadratic and be outside of the circle. So outside the circle and inside the quadratic is our feasible region. As this continues down, so does our feasible region. Hopefully that makes sense. Have a wonderful rest of your day.